One of the things that's always fascinated me is Bit Blit or the Blit operation and things that it's variously referred to depending on which computer system you're using, which operating system, what time of day it is, that sort of thing. This was an algorithm that was developed at Xerox PARC back in the 70s by Diana Merry and Dan Ingalls and a few others. And it's an algorithm that was used right through the 70s, through the 80s and even into the 90s on computer graphics hardware across all sorts of different computers and in software and things. And so I thought it'd be fun to have a look at what this algorithm is used for, why it's sometimes implemented in software, why it's even faster if you implement it in hardware, or can be faster if you implement it in hardware, and things, and just why it's so useful in computer graphics operations. If you bought a computer in the 80s, you may well see that listed on the features was that it had a Blitter chip in there. This was famously with the Commodore Amiga, was one of the things that they claimed made it so good. And then it was added by Atari into the Atari ST line a bit later on as well. And that is just a hardware implementation of the same algorithm that Xerox PARC and others have been using right back to the 70s. So it's not something new that came from Commodore or Amiga or any of those things. It's just implementing a standard algorithm in hardware because it works faster if you do it in hardware than if you do it in software. So what does this algorithm do? Well, it's very, very simple. It copies blocks of memory from one location to another. But it has the ability to combine those 2 blocks or 3 blocks, depending on the way you implement it, in specific ways. And depending on how you combine those things, you can get interesting patterns appear on screen. So it's mainly used for graphics operations, although you can use it for other things. The Atari Falcon, for example, uses it to speed up hard disk access because your hard disk appears as a location in memory, and so you can copy from that location to other bits of memory very, very quickly if you use the Blitter chip to do it. But in general, it's used for graphics operations. So let's remind ourselves about how a computer would represent graphics display in its computer's memory. And we're going to think about a very, very simple one. We're going to sort of go down to the bare bones. We're going to have a set of pixels. Well, let's just do it with 4 by 4, so I don't have to draw so many squares. So 1, 2, 3, 4 rows and 4 columns of pixels. So we can reference any pixel on that by giving it a number. So we've got 0, 1, 2, 3 for the rows and 0, 1, 2, 3 for the columns. And then we can start to draw shapes in there. So if I want to sort of square, I can fill in the first 2 pixels on the first row, fill in the first 2 pixels on the second row. We're going to keep this simple. We're going to have pixels that are either black or white, on or off. Now that's fine. We can draw things and we can start to draw interesting patterns. Let's do the same here. But we need a way to encode that into the computer's memory. And the way that we do that is that we can convert these pixels into bits of the computer's memory. And we can do that and say, well, okay, a black pixel is going to be 1 because it's set, and a white pixel is going to be 0 because it's not set. So we could take the first row, and so we're going to represent that as a 1 bit because we've set it, a 1 bit because we've set it, a 0 bit because we haven't set it, and a 0 bit because we haven't set it. Next line's exactly the same. And then we can do the same again for this line, not set, so 0, 0, set, that's a 1, not set, that's a 0, and we've got an interesting pattern, I don't know quite what it is. And then on the last line, not set, not set, not set, set. And so we can convert the patterns that we've created into a binary number, and then we could store that in the computer's memory. So this would be the equivalent of, what's that, that's 12, 12, 2, and 1, and we could store them in the computer's memory. If we want more pixels, so if we would say go to have 8 pixels, we'd use 8 bits. If we wanted 16 pixels, we'd use 16 bits, 2 bytes, and so on to store that. And what we do is we'd store this starting from the top of the screen with the first line. We store all the bits that may represent that. So let's say we've got a 640 by 480 screen, we'd have 640 bits, 80 bytes worth of information. 80 times 8 is 640, 8 bits in a byte, 8 pixels in a byte. 80 bytes would represent that line. Then the next 80 bytes in memory would be the next line of pixels, and that will continue for 480 lines, and 32K of memory later, you've got the data for your screen. Now that works very nicely. You can store it in memory. The other thing is it's actually very easy to build the display hardware to display that on screen, because you can take a byte or a word of memory at a time, load it into the sort of same shift registers that Mike was talking about last week when he was talking about linear feedback shift registers, hardware implementation of that. You load the byte in and then you clock out each of the bits one by one out of the shift register, and that's the signal that you can send to your TV or whatever monitor device you're using to display things on screen. So this approach works really nicely for storing data in a form that we can manipulate, because we can just change the bits to change the pattern. So for example, if we wanted to invert this pattern here, so rather than having black, black, white, white, we had white, white, black, black, we could take the bits, run them through a NOT gate, and we'd invert it so we get 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, and if we draw square out again, so there we are. So we can manipulate those bits to change the pattern that we've got on screen. And what we find is that you can use various operations to alter the bits as they're stored in memory to create different graphical effects. So for example, if we wanted to draw a character on screen, let's say we wanted to draw a character, let's go for a letter A, and I'm going to draw an 8 by 8 this time, so we'll go a bit bigger. So we can represent this, and we've got a letter A as an 8-bit character. In the same way, we can convert this into a series of bytes that we can store in memory. So we've got 0 across the top because none of them are set. I'm speeding things up. We've got 60 in there. If we convert it to binary, that's 64 plus 2, that's 66. 66, that's 126. We'll go with 66, 66, and we've got 0, and we can fast forward through that as well. And we've got a series of bytes that can represent a character A. And we can display that character on screen just by going to some location and writing those bytes into the memory that's representing our screen one row after another. So we have to write it at the right location, the right byte in memory, then add on the length of the screen line, as Mike's talked about in some of the videos on images, write the next byte in, and then you go down, and that would appear on screen.
Is this what's known as a screen buffer?
Yeah, exactly. This is the sort of the way that the screen buffer is. It's just literally a series of bits that represent it in memory. And actually, one of the things you find is when people started to add colour, rather than say using 2 pixels next to each other, which you could do, or 3 pixels, 4 pixels to represent, they use the same idea of having a bitmap display, but then they put another one behind it, and you read the colour by looking at the first plane of bits and the second plane of bits behind it. So this might have a 0, that might have a 1 in the same location for a pixel. So that's your colour. The pixel is 0, 1, colour 2. Okay. So we can write those bytes into memory at that location, and that would display them on the screen. Except what we'd end up doing is we would replace what was on the screen beforehand. So we'd always get a letter A, but it would all be on a white or black background depending on what way you got the colours. But what we could do is we could use a different way of storing them. So we could actually say, and I'm going to be clever here just to try and illustrate this if I can figure it out. Let's say we wanted to draw a line to show that this had been crossed out. And we could do that by having a line, and we'd represent that just by a series of pixels, one after the other, going in a diagonal pattern, and we could work out the bit pattern for that. And we'd start off with 128, 64, 32. I'm not going to bother going through that. So what we want to do is to overlay that on top. If I just take the numbers and write them, we don't overwrite what was here. But what I can do is I can take the number I've got here and combine it with the bits that I've got already on the screen. So what I can do is I can take the number here, which is 128, combine it with the number we've got here using the OR operation, and basically all I'm doing here is ORing every bit here with the equivalent bit in the other one. So that would then become 0 or 128 is 128, and then that would set that pixel there, leaving the rest things. Do the same with the other one, so we get 64 here, 60 or 64 becomes 124 in that case. We now do the next one, we would have 32 and we'd OR that in there. 60 or 32 is going to be 96 and so on, and we can work out the numbers and we can do the same thing.
So just to check, so the OR operation there is saying if it's not already a 1, make it a 1.
Yeah, so it's exactly the same Boolean logic that you've seen in computer science before. You take 2 bits in the same position, you run them through an OR gate. If either bit is set, or both bits, then the output is 1, otherwise the output is 0 if both bits are 0. So you could do that. You could also do the same using AND, and you'd get interesting effects where you'd mask off some pixels. So you'd only have the pixels set where both the original image and the new image had a pixel set there. And if you draw the right shape there, you could say have one image that was a circle, another image which was something, and them together, and you'd end up with whatever the first image was now in a circle. So what we find is that we can write software which can combine the things and to draw things on the screen. If we want to copy a value on and just replace it, we can just store the values in there. If we want to overlay them, we can OR them. If we want to sort of mask them, we can use an AND to do that, and various other things. We can invert them by running them through a NOT gate. So various Boolean operations, Boolean logic operations can have interesting effects as to what appears on screen. Now, you can write the software to do that, but what actually turns out is that most of these operations end up looking the same. Let's say I want to copy this is my screen, an image over here. Let's say we've got a picture of a dog. Well, that's my image of a dog. And I want to copy it to appear down here. Now, how would I do that? Well, I would start off reading in the bytes that make up this dog in the corner, look at the number, copy 0 there, and I would copy the same bytes there, then do it for the next one along, the next one along, the next one along, the next one along, the next one along. In fact, you do it bit by bit because you're copying the bits and things, and then eventually you'd get to the bits that sort of make up the dog. I don't know if that looks like a dog. Let's have a little bit more. It's vaguely like Gromit, isn't it? Looking straight end on.
Maybe if it had a couple of eyes, it might be more.
You're testing my graphical skills here. There we are. So that's a dog, and we copy it by basically copying all the bits from one location to the other. And to do that, we find out where in memory this starts, and we find out how many bits it's taking up, and we copy those bits here to this new location. Where are we putting them? Well, we find out where this starts in memory, and we copy them to this things, and we start writing the bits there. Now, the interesting thing is that you can have 2 rectangles here, 2 regions, and they might be different sizes. So you might say, copy this rectangle here to this rectangle here, which is slightly smaller. And in that case, you want to work out, okay, this one's smaller. I'll stop when I get to the edge of this one, then move on to the next line. So you can work out, we'll keep them the same size just to simplify things. So we can do that in a for loop. We go across the top line, copying all the bits one by one. And to speed it up, we'd probably copy the bytes. But the problem with that is that that's fine if they line up on a multiple of 8 or a multiple of 16 if your computer works in short words and things and so on. But if this is, say, at position 8, we can read it easily, but we want to put it at position, let's say this is 322, shall we say. That doesn't line up to a multiple of 8. The nearest multiple of 8 is 320. So 320 bytes in from the middle of the screen, but actually we want the bits to start 2 pixels further on. So actually what we need to do is take the 8 bits from here, move them here. We don't want to write them exactly. We sort of shift them right by 2, which means 2 bits fall out the edge, and we have to keep track of them. And then we write that byte into memory. And then we've got 2 bits left over from the previous byte, which we need to get to now be in the top 2 bits of that byte. And we copy the next bit in, and so it ends up, we can write the software to do this. It's relatively straightforward code. And we just step through this, copy them across. And then we go on to the next line. We update our pointer here to get back to the position here. We update the pointer from the rectangle here to get to the next line, and we do exactly the same thing. And if you want to write a character on the screen, you do this, but you just store the values. If you want to overlay them, you do the same thing, because this source rectangle doesn't actually have to be on the screen, it just has to be somewhere in memory. And the same operation applies. It could be a different shape screen, you just add different values on, and so on. So what the Bit Blit algorithm does is, it basically is a way of automatically taking one source rectangle. So we can take all the pixels from here, and we describe where it is with things from where it is in memory, because memory is memory, The way we make it into an image is the way that we describe that memory and treat it in our software and then the hardware that displays it. So this doesn't have to be the same location in memory. As long as we know where it is, we know how long a width of the screen is, width of that block is in pixels and bytes and things, we can describe that. And as we know where this is going, they can overlap and things. We can then copy it. If we just want to copy it from one location to the other, we read a byte, write it at the right position. If we want to overlay them, we read a byte from the source image, all them together, write them back, having shifted things if we need to get them in the right place. If we want to mask them, we do the same with an AND. The Bit Blit algorithm just generalizes this. So you can then use this algorithm to copy from one region somewhere in the computer's memory to another, applying whatever operation, whatever combination of logical operations you want to do. And as we said, there's only a small number that actually makes sense. There's only 15 that you can do. So there's only 16 that you can do, 2 of which set things to all be 0 or all be 1, which you don't really need to do because you can just copy from a black bit or a white bit of the screen and so on. So yeah, there's a limited number that actually makes sense, but there's only 16 that you could possibly do anyway. So that's the Bit Blit algorithm. It's just a way of copying things about and combining them to create fancy images. Now, why did this all get implemented in hardware? Well, the problem is that when you start to write software to do this, you actually have to write a program that's run by the CPU that does this thing. You could think about a very trivial operation where you start, okay, get the first pixel, work out where that is on screen, work out which bit is representing that, read that bit, move that so it's in the right place to set the bit on the screen at the other thing, combine it with the bit that's already there based on the operation you want to do and things. If you do that, there's a famous paper by Rob Pike describing how this works, and they implemented it on a 68000 back in the 80s. It took 8 minutes to copy a screen, which is a bit slow, but you can do it. But there's ways you can speed it up. As we said, you could read a byte at a time and shift that byte to the right place and then write a byte at a time. You'll get 8 times faster because you're reading 8 bytes, or you can do it in 16s if you've got a 16-bit machine and so on, and get 16 times faster, roughly. But if you actually look at what's happening, if you were to write a program that was do it, the way the CPU works is the CPU is going to read the instruction it's going to execute, particularly on the CPUs of the time. These days you've got caches, as we talked about in there, which will actually sort of save it having to read that from memory again. But the way this operation works does cause some interesting issues with the cache operations if you don't have separate instruction and data caches, because you're reading lots of data and so you're going all over memory and things, so it's not cache friendly. So you read an instruction which says load a byte from memory, you load it and you manipulate it and you store it, but each of those operations requires another CPU instruction. So actually what will end up happening is that your CPU is spending most times fetching the instructions to execute rather than fetching the graphics images and manipulating them. So what people did, because this is actually a very structured algorithm, it's read byte from memory, combine bytes, write result back to memory, increment pointers, repeat until you get to the end of the line, increment pointers in a slightly different way, rinse and repeat for the next line, and so on. It's actually very easy to build this in hardware. And so what the Blitter chips were in the Amiga, what the Blitter chips was in the Atari ST and other computers, were hardware implementations of the Bit Blit algorithm. And by implementing it in hardware, you can get a huge speed increase, because that chip is, all it does is Bit Blit operations. So it doesn't have to fetch the instruction to say load the byte from memory, then load the byte. It just knows that it's loading it from memory, loads that byte, loads this byte from the destination, combines them, writes it back out to the destination, gets on with the next one. It's a fixed processor. It does one thing and it does it very, very quickly. But also, if we think about, we talked about how, if this is at pixel 8 and we're moving it to pixel 322, we have to shift it about, and then we've got the bits left over and things. You can start to do clever things in your design. Let's draw out a register, just a bit of memory inside the chip with 8, 1, 2, 3, 4, 5, 6, 7, 8. What we can do is read in each bit from that byte into memory. Now we could have a shift register where we actually shift it about, but there's actually a clever way that we can do this, which is what some of the Blitter chips did. is that we can have another 8 bits, and I'm going to draw these slightly smaller. 1, 2, 3, 4, 5, 6, 7, 8 there, which line up next to it. And when we start at the beginning of the line, we set all these to be 0. Either all blank, or all ones, depending on how you're doing it, doesn't matter, we'll just say 0. And then when we come to actually, we load in these bits with the ones for the pixels. So let's say we're copying that letter A, which we had over there. We're on this line, so we're going to load in these bits starting from this. So we're going to have a blank one, we're going to have a 1 in it, and we've got 1, 1, 1, 1, 1, 0, or something like that.
Close enough.
Close enough, and things in there, we've got a 0 there. Now let's say we want to shift this 2 places to the right. What we actually do is we don't do any shifting at all. We just say, well, okay, well, we'll read the most significant bit, bit 7 from there. So that becomes bit 7 that we use. We read bit 6 from here. Then we can read bit 5 from here, bit 4 from there, bit 3, bit 2, bit 1, and bit 0 from there. Okay, no need to shift it. We can just select those bits in hardware and send them to the output. And what we do is we could have, if we want to shift it by 3, where we start here and read it. And we just have basically a switch inside. So imagine the sort of rotary switches. You have the sort of digital equivalent of that, which selects where it wants to read them from.
So sort of shifts this across and just moves it.
So we shift the answer back, because everything we're going to copy is going to be shifted by the same amount. So rather than shifting the input, we just shift where we read the output to the left, and we get the same effect.
What do we do with those leftover bits?
Now this is where it gets clever. So we've got these 2 bits left over. So we read the first byte, we shift it by shifting our output things, and then we've wired this up. So when we come to read the next byte, as it loads in those bits there, all these bits get copied 0, 1, 1, 1, 1, 1, 1 into these bits over here. Because now when we read in from the same place, bit 7 has got what was bit 1 over there in the top bit. Bit 0 has gone into what was bit 6. Those things are copied in there. So again, we can build the hardware to enable us to copy these things very, very quickly. So we can design this into the Blitter chip, whether it's the Amigas, whether it's the Ataris, whichever one it is, by using clever hardware and just selecting different positions and so on. And then you can write them out. There's the bytes or the words that you're going to write out to the screen. So the Blitter chip can do this much quicker than you could do it in software. And in fact, you can optimize it even quicker. Some of them will say, well, actually, you've selected a mode where I'm not actually combining anything. If I'm just writing the value in there, I don't need to read the destination's value. First, I can just use that things, and then you can combine it. So that's Bit Blit. It's an algorithm that was developed on the Xerox Alto machines for copying regions. It was made popular in Smalltalk as well back in the early 80s. And then the computers of the 80s and into the 90s were using this type of operation to sort of composite all their graphics together. If you wanted to copy some text on screen, you would use a Bit Blit, except you might not, because one of the problems with it is it's great when the regions are big, because the setup cost is quite small. You have to set up, I want to copy from this block of memory, it's got this size and dimensions things, to this block of memory, it's got this size and dimensions and things. That takes time. If you're just copying a single character, 8 bytes, it's often quicker to just do that manually on your CPU, because the cost is similar to do it manually as it would be to set it up. But if you want to copy a window from one side of the screen to another, or you're scrolling a whole line of text in Microsoft Word or something where it's a lot of text, it's much quicker to do it using the Bit Blit algorithm.
And I'm assuming, judging by the machines you've talked about, that this was used a lot for gaming and adding kind of characters onto backgrounds and things like that.
Yes, that's exactly. I mean, one of the things that the Amiga did to act as a good games machine was that the Blitter operations could copy Blitter objects, bobs as they were called, around the screen as they needed them to draw them on screen very, very quickly. It would set up the Blitter to do it, and often this could run in parallel to the main CPU. So the Blitter could be copying data while you calculated where the next one was going to go, and then put it on screen in some form. There's limitations because you can't have 2 things accessing memory at the same time easily, but you can get some small form of parallelism in there and so on to do it. The problem these days, why it's perhaps not used as much, is that, as we said, when you've got continuous tone images, sort of grayscales, 24-bit, 32-bit color, you don't want to be doing bit operations to combine things. You have an alpha channel, which is a sort of value between 0 and 1 mapped into a 8-bit or 10-bit or 16-bit value, depending on your image system. And you would then do similar things in that you would take the source image and you would multiply it by its alpha channel. You'd take the destination image and you would multiply that by 1 minus the alpha channel, and then you would add them together to get the same sort of effect. So you can sort of think about some of these operations being done in Boolean logic as being sort of alpha channels where they're forced to be either 1 or 0, and then we can do it with logical operations.
Do not try this at home.
No,
absolutely.
only try this at home.
Oh, yeah, that's a very good point. Try this at home, but not anywhere else at home.
In some sense, remember when we talked about 3D images, you could view RGB as in some sense 3D. So the first plane is R, G and B, or vice versa.